Welcome to ePathshala lecture series on computer science. In this module on data analytics, we will be discussing about regression analysis and its application in analytics. So, the objective of this modules are: first, let us understand the fundamentals behind regression analysis and the various types of regression analysis. Then we need to know what is the difference between regression analysis and correlation, and this difference will clearly help us to understand how analytics and inferences from analytics may be varied. And finally, as part of this module, we will be discussing about understanding simple linear regression with an example. So, to start with, let us first understand what is regression analysis. Fundamentally, regression is a statistical technique, and in this statistical technique, what we are trying to identify is we are trying to determine the linear relationship between two or more variables. Whenever we end up with a data set, the data set has lots of attributes associated to it. All that we are trying to do is we are trying to identify, is there any interrelationship that is exhibited by these attributes, and this interrelationship may be used for the purpose of arriving at conclusion. So, regression analysis is one such technique that will help us in determining the linear relationship exhibited by two or more variables. Regression primarily is used for prediction and for causal inferences. So, how we can represent regression? To be very simple, regression for say a bivariate environment, bivariate here in the sense there are two random variables, say for example x and y. We try to exhibit the relationship between these two random variables x and y by means of a simple equation. The equation will make use of the two variables x, assume x is the variable which is independent and y is the variable that is dependent on x. So, therefore, regression or the linear relationship between the two variables x and y may be represented as shown in the given equation. Y is equal to beta naught plus beta 1 x plus u. Here in this equation, you may find x as the independent variable and y is the dependent variable, that is, which is determined based on the value of x. Apart from x, we have other constants like beta and beta 1. The magnitude and direction of the relation is given by the slope parameter. The slope parameter is indicated by the beta 1 value. Beta naught is actually say the intercept parameter. This intercept parameter helps us to understand what is the status of the dependent variable when the independent variable is absent. And the last parameter u fundamentally is an error component. Whenever we are trying to model a particular problem using regression methodology, there is lot of chance for what we predict and what has actually been observed, and this difference need to be added to the given environment by means of an error variable. So, the u variable in this equation indicates the error component, and the regression coefficient, which is commonly indicated using the notation r square, shows how well the values fit the given data. So, with this understanding, let us understand what is regression and how it is different from that of correlation. Regression actually helps us to show what is the variation in one variable with respect to the variation in the other variable, and what regression will not help us is it will not show causation. For example, consider two variables. One is say for example the size of a shoe, another one is the size of say foot. Now, we may have lots of shoe sizes and we may also have lot of foot sizes. The shoe size can be treated as an independent variable and the foot size can be considered as a dependent variable, and when you are trying to identify the regression or when you are trying to determine the linear relationship between these two variables, we may find very high regression coefficient and highly significant parameter estimates, but with this we cannot come to a conclusion that the foot size is determined by means of the shoe size. The reason is they may be linearly dependent, that is the independent variable shoe size may determine the foot size for the given problem, but when we are trying to analyze from a logic perspective, the reverse may not be true. In other words, the shoe size cannot cause the foot size, that is a variation in the foot size. So, we cannot say that if there is an increase in shoe size, it indicates there is an increase in the foot size. This is wrong. So, that is the reason why I mentioned regression cannot show the causation. So now we can clearly know what is the difference between a regression and correlation. So we need to fundamentally understand that both are two different things. So with respect to correlation, what we are trying to identify? Correlation actually determines the strength of the relation between variables, but regression fundamentally attempts to identify what type of relation do those variables exhibit. But when we take a look at regression, it actually provides more or in-depth knowledge about the relation. So correlation is trying to identify the strength, and regression goes one step more, that is, it provides more details about the relationship among the variables. Now let us take a regression model. We will analyze what are the different types of regression models available, and then we will learn one type of regression model using a simple example. So there are various ways by which you can classify regression models. Here in this environment, we will be classifying regression models into two types based on the number of parameters used for analyzing. If we are going to make use of one explanatory variable, then we consider those regression models to be simple regression models, and if we involve two or more explanatory variables, then we treat those models to be multiple regression models. Even under simple or multiple regression models, we can further classify them into linear and non-linear. Let us first understand what is a linear regression model. A linear regression model is associated to two variables. In other words, it is associated to a bivariate environment. So this is the most simplest form of regression analysis. So here in linear regression model, we consider a pair of variables that appears or which is going to be part of the data set, and we are trying to establish what relationship do they exhibit. When we are considering multiple linear regression model, what exactly we do is, we design a multiple linear regression model to study or to determine the relationship between one variable with respect to several other variables available in the data set. Whether it is a multiple linear regression or a simple linear regression, in both the cases, the sample is considered as a random sample from our original population. The two variables x and y are two measures or the measured outcomes for each observation from the population set. So we are going to take a population, from that population we are going to extract a sample, and from the sample we are going to identify the x and y, which is going to be the measured outcome for the given population, and with that we are going to do regression analysis. So a linear regression model, ultimately we are going to define an output function, or the output of a linear regression model may be a function. This function will be useful for predicting the variable that is dependent on another variable, and to what extent the dependent variable is determined by the independent variable. For example, we can consider this as a simple straight line equation. As shown in this diagram, we have two variables x and y. X is the independent variable and y is the dependent variable. Now we have set of outcomes which are nothing but the sample data. For this sample data, we can always define, say, a linear regression with respect to this equation, y dash is equal to beta naught plus beta 1 x plus or minus epsilon, where epsilon is the error, x is the independent variable, and y dash is actually, say, the expected or predicted output, or the variable which is determined by x. What exactly is this beta naught is? The beta naught is the y-intercept, and this beta 1 is the slope of the given straight line. So ultimately what we are trying to do is, we are trying to visualize the simple linear regression as a straight line fitting or a curve fitting problem. So here in this scenario, the simple linear regression fits a straight line to the given data. Now how the parameters may be estimated given the data? Let us take this simple table. In this table, we find the two variables x and y and the corresponding values given here. Now what is that we need to compute for parameter estimation is, you need to compute the square of x, the square of y, the summation of x, the summation of y, summation of x square, summation of y square, product of xy, and the sum of these products. So, with these parameters, what is that we are going to estimate? As I already mentioned, in the previous equation there are two parameters, one is the beta naught, which is the y intercept, and beta 1 the slope. So, these two things must be estimated. So, we need to determine first what is beta 1. So, beta 1 is as given in this equation. So, we need to take the product of x and y, the sum of these products, and we need to find the difference with respect to the sum of x, sum of y product divided by n, where n is the total number of values or instances here. Having done this beta 1 computation, next we can define beta naught with respect to beta 1. So, beta naught is equal to y bar minus beta 1, that is the estimated beta 1 multiplied by the corresponding x value. So, now with the example of beta 1, we can now determine what is beta naught. Having determined the two parameters beta 1 and beta naught, the slope and the y intercept respectively, now we can make use of these two values into the original equation, that is y is equal to beta naught plus beta 1 x plus or minus epsilon, for the purpose of determining or estimating the y value. Now, let us take an example and understand how this may be done. But before going to the example, we should know what is that we can infer from beta naught and beta 1. So, the interpretation of coefficients will help in lot of analysis. First, let us take beta 1, which is the slope. The slope actually indicates what is the percentage of y changes with respect to the change in the x. That is, y is the value that is determined and x is the variable which will be used for determining y. So, with respect to every change in x, to what extent y changes is what is we can infer from beta 1. For example, if beta 1 is equal to 2, then y is expected to increase by 2 for each 1 unit change in x. Similarly, the y intercept beta naught. The y intercept beta naught helps us to understand what is the average value of y provided x is 0. When x is 0, it does not mean x is completely absent, it is not so. So, when the independent variable is not taking part for the purpose of prediction, what may be the average value of y? This is what we can infer using the beta naught or y intercept. Suppose if beta naught is equal to 4, then what is that we can conclude is, we can conclude that average of y is expected to be 4 given x is equal to 0. Now, with these inferences, we can make lot of conclusions from our given data set, and these inferences will help us to better understand to what extent there is a linear relationship between the independent variable x and the dependent variable y. So, let us take an example. Consider the data given here. Assume this data is collected from a nearby cattle farm, where the intake by cows given in kilograms and the milk yield given in liters. Now, what is that we are trying to identify here is there any relationship between the food intake by the cow and the corresponding milk yield? Now, we are trying to establish a relationship which we assume to be linear between these two variables, food intake and milk yield. Now, how we can proceed? Before proceeding, we should understand by plotting this data using a scattergram. So, we can consider the two variables food intake and milk yield as two axes x and y, and now when we plot the data, we will get a scattergram as shown here. Now, from the scattergram itself, we may be in a position to identify, can there be a linear relationship or not. So, this scatter diagram will help us to identify, is there a linear relationship between these two variables. Having done this, now let us make use of the equations for estimating the parameters. So, for the given data x and y, where x is the food intake in kilogram and y is, say, the milk yield in liters, we will calculate x square, y square, product of x and y, and the sum of x value, sum of y value, sum of x square value, sum of y square value, and the sum of the product x and y. So, the sum values are indicated in this pink shaded row, So 32 is the sum of x value, 24 is the sum of y value, the sum of x square is 296, sum of y square is 162.5 and the sum of product is 218. Now all that we need to do is identify or calculate the beta 1 and beta naught. So first we need to identify beta 1. So beta 1 from the given equation we need to just substitute the corresponding values. So summation of x y product is 218. So we replace this notation using the corresponding value 218. Summation of x is 32 and summation of y is 24. So 32 multiplied by 24, the whole divided by n. Here n is 1, 2, 3, 4, which is nothing but the number of instances, input instances. The whole divided by summation of x square. So x square summation is 296 minus summation of x the whole square. So which is summation of x is 32 the whole square divided by n here is 4. So which is equal to 0.65. Having calculated beta 1, now we can calculate beta naught. So beta 1, as I already mentioned, is the slope and beta naught is the y intercept. So we can compute what is the average for y, which is y bar. So we will have to take 24 is the sum of y divided by total number of instances 4. So 24 divided by 4 is 6. So y bar, the mean for y is going to be 6 minus beta 1 multiplied by the x bar mean. So the sum of x is 32 divided by 4 will be 8, which is the mean of x. So 0.65, which is beta 1 value, multiplied by the average of x parameter, which is equal to 0.80. So now we have determined what is beta 1, which is the slope, and beta naught, which is the y intercept. Now with these two values, what is that we can infer? So now we will have to interpret the coefficients. Beta 1, as I already mentioned, indicates the slope, which clearly states to what extent the dependent variable is changed or varying with respect to the independent variable. Here in our example, beta 1 was equal to 0.65. So it indicates the milk yield, that is the y parameter, is expected to increase by 0.65 liters for each 1 kg increase in the food intake, which is the x variable. So for every 1 kg increase in the food intake, the milk yield will increase by 0.65 liters. This is what we can infer using the slope parameter beta 1. Then with respect to beta naught, which is the y intercept, as I already mentioned, it is the average value with respect to the absence of say x, that is when x is equal to 0. Suppose the food intake is going to be 0, then what will be the average milk yield? So the average milk yield will be 0.8 liters, which was the value for beta naught as we computed earlier, indicates the average milk yield is expected to be 0.85 liters when there is no food intake by the cattle or the cow. Now this is what we can infer using the values beta 1 and beta naught. Now with these two values, what is that we can conclude is there is a level of linear relationship between the two variables, food intake and the milk yield. So such relationship may be further used for decision making or for further analysis. Now whatever may be the scenario, we are trying to take the data and we are trying to fit to a straight line. When we are trying to fit the given data to a straight line, there is always a chance for the straight line not to cover all the observed data. So we need to identify what is the difference with respect to the given straight line and the observed values, which may be quantified in the form of error. So all that we need to do is identify the error and use it for further analysis. So in the given scenario that we discussed earlier, we may end up with a straight line which will be defined by the beta naught and beta 1 for every x value. Now when you fit the line, you will find the dark colored dots, black colored dots indicate the actual data, but the line that we have fit does not cover all the data. In other words, few of the data does not lie exactly on this line. What does it mean? Whatever we have predicted has some difference with respect to the observed value. Now, this difference is called as error. So, we need to define a function that will quantify the error which may be associated to the linear equation for effective or accurate prediction. So, we need to define a function which will make a prediction for each and every observed data point, and the observation that you make is indicated as y in this diagram, and the prediction that we make using the equation, linear regression equation, is y dash. Now, what is that we need to do is, as I mentioned, you need to predict the error. So, how you can quantify the error for each and every observation is, error for each and every observation may be defined by this characteristic equation, y is equal to y dash plus epsilon, where y is the actual y value, y dash is the explained y value or the value that we have predicted, and epsilon is the error. So, how to quantify this error and how to take an account of this error? Normally what we do is, we quantify the error using sum of squares of error. What exactly you mean by sum of squares of error is, given the line which you have fit using the given variable, say x, we can always identify what is the difference of the observed data with respect to this straight line. So, there will be a distance between the observed variable and say the predicted variable. Now, this difference can be squared and summed, and the entire sum can be treated as the sum of squares of error, which is in short called as SSE. So, in least squares regression, what we do is, we select or choose a line which might reduce this SSE error. The other way of doing is, given the straight line that we have fit and the observed value, we can always take the population mean, say the dependent variable y, the corresponding population mean is represented using y bar. Now, all that we can do is compute the difference of each and every observed variable or value with respect to the population mean. So, take the value y and identify its difference with respect to the population mean y bar. Now, this is going to be an error. This error can be squared, and the sum of these error will result in SSR, which is called as sum of squares regression. So, this will provide a complete detail about what is the difference between the prediction for each and every observation and the population mean. Now, having determined this SSE and SSR, we can now compute what is the total sum of squares. The total sum of square SST is the sum of SSR and SSE. As we have already discussed, SSR is the measure of explained variation. In other words, we try to identify the difference between the mean and say the predicted value. SSE determines the difference between the actual value, that is the observed value y, and say the predicted value. So, SSE is a measure of unexplained variation and SSR is a measure of explained variation. Now, these two errors need to be summed for computing the total error. So, SST is equal to SSR plus SSE, which is equal to summation of y minus y bar the whole square. Now, we have determined SSR and SSE. Now, the ratio between these two may be used for quantifying coefficient of determination, which is R square. So, R square is actually a proportion of total variation SST with respect to say the explained SSR. In other words, or mathematically we can represent R square, the coefficient of determination, as the ratio between SSR and SST. Since we know SST is the sum of SSR and SSE, this coefficient of determination will be equal to SSR divided by SSR plus SSE. And this value R square may take any value in the range 0 to 1, and higher the value of R square indicates the model that we have defined, the regression model that we have defined is more accurate or good. So, it is often referred in the form of percentage, which quantifies to what extent the regression model is more accurate. So, these parameters like SSR, SSE and SST together with the coefficient of determination R will help us to identify or determine the accuracy of the regression model that we have defined. Apart from the regression determination coefficient, we also have a standard error for regression. Standard error is actually a normalized error, and this normalized error is with respect to SSE, sum of squared errors. So, the standard error is as given in this equation, square root of SSE divided by n minus k, where n is the number of observations in the sample and k is the total number of variables that we are using as part of our model. So, this ratio actually provides a clear indication of to what extent there is a variability of one variable with respect to another variable. So, this variability, this measure of variability will help us to understand to what extent our prediction may be accurate, and we normally can determine the accuracy based on say y plus or minus 2 standard error means normally it will provide an error which is very less, and we may get an accuracy up to 95% accuracy. Suppose we are using say 3 standard errors, so y plus or minus 3 standard error means we may end up with 99% confidence interval. So, the percentage of the standard error will help us to understand to what extent our model is accurate or not. Having understood say a linear regression model, now let us understand what is a multiple regression model, how it may be defined. So, when we are trying to make use of more than one independent variable, and when we are trying to analyze this independent variable with respect to another dependent variable, then we will be ending in a non-linear environment. To be very simple, we take more than one independent variable and we try to model it with respect to one dependent variable. So, multiple regression may be mathematically represented as shown here. So, y is equal to a plus beta 1 x1 plus beta 2 x2 plus beta k xk plus epsilon, where k is the number of variables that we are considering for our analysis. This multiple regression may ultimately result in multi-collinearity. Multi-collinearity is a condition in which at least 2 independent variables are highly linearly correlated. That is, we may have minimum 2 or more than that number of variables that are highly linearly correlated. So, now there comes a confusion, should we consider the first variable or the second variable for defining our linear regression model? In such scenarios, we will have to make use of additional knowledge for selecting say a particular variable for defining our linear model. For example, here in this table we find y and 2 other variables, independent variables x1 and x2. Now, we find x1 and x2 are having only minor difference with respect to their correlation for y. So, here we may be in a confusion whether to choose x2 or x1. So, what we can do is we normally go by a rule which is stated by many data mining experts. So, any independent variable which has a correlation which is more than 0.3 but less than 0.7 will be included for the purpose of prediction. So, when we have more than 2 linearly independent variables which are highly correlated, then we will have to choose the one that will help us in effective prediction. Apart from linear environment, we may end up with say a nonlinear environment in which we may come up with functions that are completely nonlinear in nature. Such environments or regressions are called as nonlinear regression. Few of the functions that may be used for nonlinear regressions are power regression, exponential regression, logarithmic regression, logistic regression, etc. So, all that we need to do is we need to define an appropriate function, power function or a logarithmic function or whatsoever, and then we need to define the nonlinear regression model. So, in this module about regression analysis, we discussed how regression may help us in identifying or determining the variation in one variable with respect to another variable. We also understood how errors in regression model may be predicted and how it may be used for compensating the accuracy of our model. And finally, we also had an introduction to nonlinear functions which are continuous and which such continuous function which may be used for the purpose of determining linearity or correlation among more than one variables. Thank you.